Hello everyone, I hope you are doing well. So in today's video, we'll be going through the 2019 physics exam for the Northern Hemisphere. Like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. And yeah guys, let's smash through this video. Question 1. Two identical bar magnets are placed end to end as shown below. Point X is midway between the bar magnets, okay? Which direction best shows the direction of the magnetic field at point X? Okay. Let's just draw magnetic field lines between the magnets. So we know this is a north to south, and you know, they're going to be attracting. So north is where the field lines come out, and they will go through the south, so they'll be going left, right. We'll also have this over here and this. These are the field lines that should pretty much be happening. Beautiful. Where you're going from north to south, the arrows go from north to south, and that's what should, yeah. So which direction measures the direction of the magnetic field at point X? As we can see at point X, it's actually to the right. The arrows are on the right. So B is showing to the right. So B is your answer. Done. So a power line carries a current of 100 amps DC in the direction east to west. So east to west. And so it's carrying 100 amps. At the point of the measurement, Earth's magnetic field is horizontally north. So horizontally north. So this actually, we want to draw it like this. So imagine these are your scales. So this is your north, this is your south, because that's and this, as you can see, it's kind of horizontal, and this over here should be your east and your west. And let's actually draw them using these over here, because it says horizontally north. North is now horizontal. So it says the power line currents of 1000 A DC in the direction of east to west. So east to west means like this. This is 1000 amps. At the point of measurement, Earth's magnetic field is horizontally north. So this is what's happening. And it's 5.0 times 10 to the negative 5. That's your magnetic field. And yeah, whichever following best gives the direction of the electromagnetic force on the power line. Easy. We're going to be using the right-hand slap rule. We know our thumb's going to go to the direction of current, and our fingers are going to go to the direction of the magnetic fields. As you can see, your palm should be going vertically downwards. So, like this. There we go. So, D is your answer. The magnitude of the force on each meter of the power line is best described as, so easy, we know that force is equal to N length times current times B, where of course it's a wire, so it has N's 1. The length is each meter, and each meter is just 1 meter. The current that runs through that is 1000, and the magnetic field is 5.0 times 10 to the negative 5. And that's going to give us our force, which is 5.0 times 10 to the negative 5. That gives me 0.05, which is 5 to the power of negative 2, which looks like that's your answer. Easy. Question 4. The gravitational field strength at the surface of Mars is 3.7. Which of the following is the closest to the change in gravitational potential energy when a 10-kilogram mass falls from 2 meters above the Earth's surface to Mars' surface? Beautiful, nice and easy. You just need to use gravitational potential energy is equal to mgh. Because G is going to be constant, it's actually on the surface. And so what's the mass? It's 10. G is actually 3.7 because that's the G value, that's gravitational field strength at Mars. And H is the height, which is 2 meters. And this is going to give us our energy. Times 3.7 times 2. And that gives me 74, which is D. So let's look at this. Use the following to answer 5 and 6. Okay. A light globe operates at 12 volts RMS AC. Okay. That is supplied by a 240 volts to a 12 volts transformer connected to a 200 volts RMS main supply. Okay. So imagine that we just draw a transformer. over here. So we know it's converting 240 volts, actually RMS, to 12 volts RMS, where it's used to operate like a light. So imagine a light here, it's used to operate that light. And we have a actual battery, and it's AC, which is, which provides 240 volts RMS. Done. In the transformer, the ratio of the turns in the primary input to the turns of their secondary output is E. This is a beautiful question, actually, because it's very easy to do. Because we know, this is what we want to find. We want to find the ratio of the primary number of coils to the secondary, which is just equal to the volts in the primary to the volts in the secondary. So if we just find this, it's equal to the ratio of this. So V1, which is the voltage in the input, which is 240 in this case, will be dot dot. V2 is the output, which is 12 in the transformer, which is 20:1 ratio. Nice and easy. I believe this actual question was in last year's exam. I think it was 2018. Yeah, multiple choice section. So this is one of the most kind of common question you'll get, and it's very, very easy. Question 6. If the light bulb is to be operated using a battery instead of a main supply, here is an important thing. It is a battery. So a battery is DC now. We're dealing with DC. So imagine drawing the same thing, but now you rub this out and you actually have a battery. Something like a battery. So DC. Instead of a main supply, what voltage should the battery have for the light to operate correctly? Nice and easy. Okay, we don't actually... No, we just need... Yeah, so we need 12 volts RMS for the light to work properly. Yes. And you should know that the voltage in RMS is actually equal to the voltage in terms of DC. So if we know that the light globe works properly when it has 12 volts RMS AC, we know that voltage RMS is just equal... So volt RMS AC is just equal to the voltage in terms of DC. And that's why we use RMS to kind of show you the relationship between the voltage in the AC to DC. And yeah, so we just need pretty much 12 volts. We need 12 volts to run it properly because it's already in RMS. So that's nice and easy. Beautiful. Question 7. Have a look at this. So let me just use a different color. Oh, this. An alternator is rotating at 12 revolutions per second. Its output is measured by the oscilloscope. The signal produced is shown below. The alternator is then slowed so that it rotates at 5 revolutions per second. So what we've done is we've slowed it down. Hence, we've pretty much doubled the time it takes for a cycle. So we doubled the time it takes for a cycle, meaning that we've doubled the period. We doubled the period. Remember, the period is how long does it take for one cycle to occur? Which of the following best shows the display observed on an oscilloscope? This is one of the most kind of common questions. So we know that EMF is actually equal to N times change in flux over change in time. Because we've doubled this time here, as we said, we've doubled the time. Imagine doubling this time. This means, sorry, that is like a multiple. So yeah, if we've doubled the time, this will halve our EMF, our voltage. So say, for example, this is 1 and that's 2. We've halved it, so now it's just 1. So our peak here, our amplitude is 1. So it'll be like this now. It'll be in over here. So, oops, what did I do? So which ones have an amplitude of a half of this distance? What's half of that distance? So let's have a look. This is doubled. As you can see, the amplitude has doubled. This one also is doubled. So yep, the other ones look good. A and D look like they have an amplitude of 1. Also, we said that the period has doubled. So it means for one cycle, let's have a look at this. This here, from here to here, is one cycle. Let's call this, imagine 2. That's for one cycle. Say in this case, the period is 2. We have doubled the period, so now it's actually 4. So which is here now. So it means for one actual cycle, it's just a full, it's actually a full, for a full cycle, it's remember the amplitude has halved, and also the period has increased double. And yeah, so it would look like this. And this shows one cycle. Which one? Looks like C is your answer. Nice and easy. This one here, the actual period has been halved. Done. So this is question 8 and 9. A tow truck is traveling on a track around a vertical loop of radius 1.6 meters, as shown below. Assume that the tow truck is a point mass, okay? The minimum speed at which the tow truck must be moving at point X for it to stay on the track is closest to what? A nice typical question. So when the truck goes over here, so let's just draw, imagine the truck's over here now. Let's actually, and we want to calculate the speed. Let's actually draw what the forces are. We know that the net force, we know that the net force is going to be acting downwards. Remember, it's the centripetal force which acts towards the center. So our F net is going to be acting towards the center. We also have the force of gravity which acts at the center. I couldn't draw it in the center because it's kind of too much, but yeah, so imagine force of gravity, which is mg. And we're also going to have a normal force that's going to be acting down. So putting these all together, so we're taking downwards as positive, by the way, because the F net's towards the down. So it's going to be F net and it's equal to mg plus n, the normal force. Now, the normal force in this case is 0 because they tell us it stays on the track. So we actually have a normal force of 0. So we know F net is actually just mv squared over r, which is just equal to mg, and those m's cancel out, which we're left with v squared over r is equal to g, and hence v is actually just the square root of rg. Done. This here gives us the minimum. This is kind of the most kind of typical question you'll get in an exam when they say find the minimum speed at which for example, something like this in this case is stays on the track. And this is the formula that you normally use, and I've just kind of transposed it and got it. All we have to do is sub in the values. So g is 9.8 and the radius is 1.6. Done. That's going to give me 3.95, which is approximately C4. Done. Question 9. Which direction best shows the direction of the resultant force on the tow track at point Z? So at point Z, what do we know? Let's just draw a tow truck. So this is where the tow truck would be. We know the resultant force is going to be upwards. Remember, it's always towards the center, which hence it's upwards, which is A, as you can see. Question 10. When light refracts as it passes from one medium to another, which of the following will change? Color? No, that has nothing to do with that. B, period? Absolutely not. C, frequency? No, when light refracts, its frequency is constant. A lot of students don't know, but it's always constant. Don't forget about that. Remember, V is equal to the wavelength times the frequency. Remember, when you have, let's say this is water and you bring light and it refracts, the actual light starts to slow down. Imagine it changes the velocity. So this here changes. Well, if F is, a constant, what would happen to the wavelength? It must also change. So the only thing that changes is the actual wavelength. Beautiful, nice and easy. Question 11. Which of the following best supports the statement that light is a transverse wave rather than a longitudinal wave? Let's see. Light can be polarized. Actually, that works because polarization only occurs for transverse waves, not longitudinal. So, great. B, light has different colors. Really? Like, what does that got to do? Like, it doesn't really explain why it's a transverse wave rather than a longitudinal wave. That's not, I wouldn't say that's right. C, light can travel through a vacuum. Yes, it can, but, it doesn't prove the statement that light is a transverse wave rather than a longitudinal wave. It's not a very great proof, so I would also put that as wrong. D, energy in light oscillates in the direction parallel to the propagation of direction. No, not parallel, but perpendicular. Be careful that one. It's actually perpendicular, so also that's wrong. So A. Yeah, makes sense. A, only polarization occurs for transverse waves, not longitudinal. So that best describes that one. 12. Which of the following statements about electromagnetic radiation is correct? Electromagnetic radiation cannot be produced by atomic energy level transitions. Yes, it can. Say, when we're looking at energy transition, say an electron goes from a high energy state, so like n equals 8, to a ground state. When it goes down, it's going to release energy in terms of photons, so which releases electromagnetic radiation. Yes, we can actually produce electromagnetic radiation. So A is wrong. B, electromagnetic radiation is only produced by atomic energy levels. No, you can produce it through other ways, like for example thermal radiation. Normally, like for example thermal heat, we can have radiation. There's many other ways you can actually get radiation, not just in the atomic energy level transition. So I want to say that, yep, B is also wrong. C, electromagnetic radiation can be produced by accelerating charges. Yes, absolutely. If you don't know, we can actually create electromagnetic by accelerating charges. So we'll put a tick on that. All electromagnetic radiation is produced by accelerating. No. This is like, then it's not going to make sense with this. You can also make, it's not just all accelerating charges. We can make it through atomic energy level transition. So also D is wrong. So C looks possible. C is the correct in this case. Yeah, beautiful. Question 13. When a mechanical wave moves through a medium, there is a net transfer of what? You should know this. When mechanical waves move through a medium, there is only a net transfer of energy. Be careful. And here's why. So imagine, like, for example, you have a wave. And say this here is like sand. And it's like hitting the wave. You know how so the wave direction is going to the right. It's going to be going and hitting the sand. So remember, the wave direction is the energy. It's like energy is propagating. But say if you have a boat here, it's the position. This is the position of the boat, and it's matter in this case. Remember, energy transfers, but matter does not in waves. So this is matter in this case, and so when the waves goes up and down, the actual boat's going to stay at the same position, but it's only going to be oscillating down and up. It's actually not going to be moving to the right, and that's the main thing. So matter does not get transferred. It's only energy that gets transferred. So let's check our answers. Mass, nope, mass is matter. B, energy, great. I'll say that's correct. Particles is matter, so nope. And D, mass and energy, nope, mass is not. So B. Beautiful. Question 14. Which of the following statements about sound and electromagnetic waves is correct? We know that sound waves are longitudinal waves, just a basic understanding, and electromagnetic waves are pretty much produced through accelerating particles. And also they travel at the speed of c, which is the speed of light, in a vacuum. A, both sound waves and electromagnetic waves can travel through a vacuum. No, we know that electromagnetic waves can travel through a vacuum, but not sound waves. It's because a vacuum does not have a medium, and for a sound wave to actually work, you need to have a medium. For example, sound waves use the medium air, so it does not work. So that's absolutely wrong. Let's put that. B, neither sound waves nor electromagnetic waves can travel through a vacuum. Rubbish, electromagnetics can actually travel through a vacuum. C, sound waves can travel through a vacuum, but electromagnetics, nope, that's also wrong. So D looks great. So sound waves cannot travel through a vacuum, yes, and electromagnetics can travel through a vacuum. Beautiful. Let's look at question 15. Monochromatic laser light of wavelength 600 nanometers shines through a narrow slit. The intensity of the light transmitted is recorded on a screen some distance away, as shown below in the diagram on the left. The intensity graph of the pattern seen on the screen is shown on the right. Okay, let's have a look. Which of the following intensity graphs best represents the pattern that would be seen if a slightly wider slit is used? So, a wider slit. This concept can actually be explained by Heisenberg's uncertainty, and here's how. So, what's going to be happening is, of course, this slit width is this, and it's going to be hitting the laser. So, and it's going to give us this pattern, this intensity pattern, which looks like approximately like this. So just have a sketch on that. It looks like this, the same as that. That's what's being produced. So let's just say this is the change, this here is the change in y, in the position of y, the uncertainty in the y direction. We know by Heisenberg's uncertainty, change in y is the change in the momentum in y is greater or equal to h over 4 pi. This is Heisenberg's uncertainty. A lot of students get confused with this kind of quantity. You know what I tell my students? Just let it equal to 1. Just let it equal to 1. That's the most basic one, and I'll show you how to use it. So, okay, this is the uncertainty in the position in the y direction. So imagine that we increase it, because remember the question says that it's slightly wider slit. We're using slightly wider. So if we make this wider, now we've increased this over here. We've increased the position, the uncertainty in the position in the direction of y. We've increased that. Now, these two products must equal to 1. If we've increased this over here, the momentum in the y direction must decrease. So that tells us that the uncertainty in the momentum in y direction decreases. So that's great, because now we are 100% certain, we are more certain that more of the electrons are going to be hitting this section of the graph. For example, when it was actually little, as we would see, when the actual slit was little, we know that, electrons or photons were actually being hit randomly. They were being hit randomly. As you can see, there's some here, there's also some here. So they were just being randomly hit. Because we increased our, slit, and now we know we are more certain that the momentum in the y direction has increased. What does that tell us? The momentum has increased, meaning that there is more now in this part over here, not in the other directions like these. It's more closer to the central maximum. So if that's true, you know what's actually the graph's gonna look like? It's gonna look more condensed. So it looks like this, but look the same, but it's more compressed. It would be more compressed because more of the electrons or photons are going to be hitting the central maximum. So it would be kind of a compressed graph. So this is the original graph, yeah? So A looks the same. That's wrong. There will be a change. Yes, B looks great. As you can see, this has gone a little bit compressed. Have a look at this. Imagine this gets compressed from the left and right, and now it looks like this. Beautiful. B looks great. C looks more spread, so that's not right. And D, I have no idea what D looks like. Yeah, that's wrong. So yeah, B looks great. Just using Heisenberg's uncertainty, that makes sense. Question 16. Let's have a look at this. In a particle accelerator, magnesium ions are accelerated to 20% of the speed of light. Which of the following is closer to the Lorentz factor for the magnesium ions at this speed? Nice and easy. So we know that the Lorentz factor is just 1 over the square root of 1 minus divided the velocity squared, which in this case is going to be 0.2 times the c value, which is 3.0 times 10 to the power of 8 squared, and 3.0 times 10 to the power of 8 squared, the c squared. So put that in your calculator and that should give you the answer. Nice and easy. So that gives me 1.02. So it looks like A is your answer. Nice and easy. 17. The lifetime of a stationary muon is measured in the laboratory to be 2.2 microseconds. The lifetime of a relativistic muon is produced in the Earth's upper atmosphere is measured by ground-based scientists to be 16 microseconds. What has happened? This here has gone through time dilation. Time has actually increased. So this part over here, this time here, is time dilation. The resulting time dilation observed by the scientists gives us a Lorentz factor of what? Nice and easy. We know that time, t, is equal to proper time times your Lorentz factor. T is the time dilated, when in this case it's 16 microseconds. We can just say 16. T naught is the proper time, which is just 2.2, and times your Lorentz factor. So to find your Lorentz factor, it's just 16 divided by 2.2, which gives me 7.3. The easy answer. 18. Let's have a look at that. If a particle's kinetic energy is 10 times its rest energy, then the Lorentz factor would be closest to what? So what's this telling us? We know that the rest energy is mc squared. And we know that the kinetic energy is Lorentz factor minus 1 mc squared. If we know that the kinetic energy is 10 times the rest energy, we can put these all together. So EK is just this, minus 1 mc squared, equals 10 E rest, which is mc squared. That mc squared cancel out, where we're left with this minus 1 equals 10, and hence your Lorentz factor is just 11. Easy. Question 19. Part of the energy level diagram for an unknown atom is shown below. Okay. Which of the following arrows shows a change of the energy level corresponding to an absorption? So we're going from a lower energy state to a higher energy state. So we're going upwards. Over photon over highest frequency. Highest frequency means the highest energy. Which one's like consuming, absorbing the highest energy? C and D are wrong because they are releasing energy as they're going downwards. A and B are great. They are absorbing, but B has a higher frequency because it's taking more energy. It's absorbing more energy. So B is your answer. Beautiful. Last question. 4 students measure the length of a piece of string. Each student takes 5 measurements and displays the results as 5 dots as shown in the diagram below. The true value is also shown in the diagram. Okay. Which student produced a set of precise but inaccurate results? Okay, precision means how close are those values related to each other? So what is the range? How close are the range of these values? Accuracy means how close is the value to the true value? So let's have a look. Look at student A. Student A over here has what? He has inaccurate because his actual answers are not accurate. They're not in that true value. Most of them are not in this true value line. So they're inaccurate. And in terms of precision, also it's not precise as the values are not closely related to each other. Their range is very large. So inaccurate and not precise. This one. Let's look at student B. Student B actually has precise results due to the fact that all these values are very closely related to each other. Their range is very, very small. So that's great. But they are very inaccurate because the true value is over here and they are out of that true value. So this is not accurate. Done. What about student C? Again, student C is not accurate as these values are not... only one value is next to the true value, but the other results, most of the results aren't in that true value. So we would consider that not accurate, not very accurate to be honest, and not precise. I wouldn't say the values are not, their range is still large, not precise. What about student D? Student B is actually precise. The range is very small, so they are very closely related to each other, the values, and it's also accurate because the true value, as you can see, those values are all on that true value. So the one that looks like gives us precise and not accurate is B. And that's it. I hope you guys learned something through this video. Please make sure to like and subscribe and send this to your peers and to help them out. I hope this video finds you well and helps you with a lot of these questions. Yeah, guys, like always, if you want private tutoring, you can always email me through that email. And yeah, guys, I hope you have a great day and take care of yourselves. Bye-bye.